Okay, so here again was our definition of winding number using these line integrals along loops. So these will always give us integers for loops avoiding z0. And so w of z0 comma gamma counts the number of times gamma winds around z0. And let's just make sure we're on the same page here. If I do the winding number of z with respect to the circle of radius r centered at z0, I'll compute this integral, which we've already done with our Cauchy integral formula on circles. And what we get is that if z is inside this disk, we'll just get the value of this function here, so we get 1. And then if z is outside the closed disk here, or z minus z0 is greater than r, then we actually get 0 because the function inside will be analytic on the disk in question. So we do get 1 for a circle, and obviously that matches our intuition. So I have the circle centered at z0 and a point z inside. We always orient our circles so that they go counterclockwise, and so the circle goes around it once if you're in there, and 0 times if you're not in there. Now let's look at some basic properties of winding numbers. So let's say I have 2 loops and they avoid the point z0. If gamma naught is homotopic to gamma 1 inside the plane minus z0, then by our homotopy theorem, the winding numbers have to be the same. The next important property is that if I have a loop, and let's define the actual set of the curve, which is just the image of the interval under gamma, then as a function of z, the winding number is constant on the connected components of the plane minus the actual points of the curve. And also for z large enough, the winding number has to be 0. If you're really far away from the curve, it can't wind around you. So that's pretty intuitive. I'll give kind of a complex analytic proof of the second property. The first property, again, just follows from the homotopy theorem because I have 2 line integrals with respect to homotopic curves. They give the same thing. For the second property, this requires a little bit of work. So let's fix a disk, a closed disk, inside the complement of the plane and the curve. And we've seen that if you have one of these continuous curves, you can make it homotopic to a piecewise linear loop inside the plane minus this closed disk. So I have my curve avoids some disk, and so to make it homotopic to a piecewise linear loop in here, well, I can just sort of cover it by disks and replace the pieces with these linear pieces, as we've seen before. And then, since it's homotopic, I can replace the winding number, at least for z's in this disk that we're avoiding. I can replace gamma with gamma tilde in our definition of the winding number because they're homotopic, and they're all avoiding the points in here. Okay, and this will be continuous by uniform continuity of the thing we're integrating. So here W is on the set of, should be gamma tilde star, so it's actual image, and Z will be in this closed disk. And so they're avoiding each other. This will be uniformly continuous, and so this integral will be continuous. And one of the reasons we're switching to piecewise linear stuff is just so that there's no issue with any regularity of this integral, because then you can do these integrals along the line segments with no problem. You could kind of get away with this with maybe more topological arguments. Okay, but this also helps us apply Morera's theorem. So then this will be analytic by Morera's theorem because I can integrate this along triangles inside this open disk, and I can switch the two integrals again because our curve is now nice, it's piecewise linear, and see that since this is analytic, the whole function has to be analytic, but it's analytic and integer valued. And so to be continuous and integer valued, you have to be locally constant. So this winding number is constant on this disk. And so if it's locally constant and continuous, then it has to be constant on connected components of the set that we're talking about. Also, gamma star is compact. So there'll be a neighborhood of infinity in the complement. And again, we can make gamma homotopic to a piecewise linear thing in this complement. So I could avoid this closed neighborhood of infinity, and then again look at the winding numbers. So they'll be homotopic, so the winding numbers will be the same. But then I have this defined on a neighborhood of infinity, and I can show that as z goes to infinity, this goes to 0. Basically, I just have to bound it by the length of gamma tilde inside the integral. And then this part here, I guess I would write it as z minus w is greater than or equal to, since points on the curve are bounded by r, then I can bound this below by z minus r, so I get this bound here, and now as I send z to infinity, I get 0 here. So as z goes to infinity, this goes to 0, but it's constant or locally constant, so it has to be 0 for all z large. Okay, and so these are the basic properties that we need to know about winding number. That doesn't change when you deform your loops, and it doesn't change when you sort of wiggle the point that you're counting the number of windings around. Now we'll put all this together in order to prove one of the most general Cauchy integral formulas.